Greetings, everyone. This is a continuation of section 8.7, and it won't be the completion of it, but it'll be trying to pick up roughly from where we left off in our notes. Since I'll be gone, this will keep us on pace with where we're headed, trying to get ready for the AP exam. And so one question that we didn't get to cover in class together was the question of finding the Taylor series for the natural log function centered at x equals 1. And then finding the interval of convergence. So let's work that one out first before we move further into our notes. And so remember, for a Taylor polynomial, or rather a Taylor series, I'll talk about Taylor polynomials in a little bit, we're going to have the first term is going to be f of a, and then we're going to have the second term will be f prime of a over 1 factorial times x minus a to the first power. And then we'll have f double prime of a over 2 factorial times x minus a to the second power. And then that's going to continue. And since I got limited screen space here, I'll just put plus dot dot dot. Every coefficient is the nth derivative of f at the center divided by n factorial. And then times x minus a to the second power. So for the problem that we're currently dealing with here, we know some things already. We know that this is going to be f of 1 plus f prime of 1 over 1 factorial times x minus 1 plus f double prime of 1 divided by 2 factorial times x minus 1 squared, and so forth on down the line. So what I need to do is I need to figure out what f prime of 1, f double prime of 1, and eventually develop a pattern for what the derivative is going to look like so that I can generalize this overall. But we got most of the Taylor series here. All we need to do is, again, figure out these derivatives, try to look for a pattern so we can represent it well, and then move on from there. So that's what we're going to start doing. So let's take a look. We're dealing with the natural log function, so we know that the derivative of the natural log function is 1 over x. And the second derivative, if you want to rewrite that as x to the negative 1, it might be helpful. And then the second derivative is going to be negative x to the negative 2. And the third derivative will be negative x, excuse me, no it won't. It's going to be 2x to the negative 3. And then the fourth derivative is going to be negative 6x to the negative 4. Now, at this point here, you might be seeing a pattern develop in what's happening here. And then again, you might not, and that's okay. You might want to extend this a little bit further. But every time we work this out, the coefficient here is multiplied by the next integer. So we started off with, this 1 that we have here, and then that got multiplied by negative 1 to get the negative 1 that we have here, and then that got multiplied by negative 2 to get this here, and then we multiplied by negative 3 to get this here, and then we're going to multiply by negative 4 and negative 5. And so, although the signs are alternating, we're multiplying by the next negative integer on down the line, and so we have a factorial pattern that is occurring here. So if we were to extend this down a little bit to the nth derivative, trying to figure out a general pattern. Well, the easy part is we're going to have x to the negative n, because the fourth derivative we had an exponent of negative 4, and then on the third derivative we had an exponent of negative 3, and on the second derivative we had an exponent of negative 2, and so forth. So that's the easiest part here. Now the question is, what about the rest of it? And I don't know if I left myself quite enough room to write this. In fact, I'm going to move over this x to the negative n. Give me a little bit of space. Well, 6 is 3 factorial, and 2 is 2 factorial, and 1 is 1 factorial. And so the factorial that I have occurring over here as the coefficient, 3 factorial, 3 is 1 less than 4. The 2 factorial that I have here to make the 2 is 1 less than 3, and the 1 factorial is 1 less than 2, so it looks like we have n minus 1 factorial as the coefficient. Okay, you could double check that in case you don't quite see it. And then we also just need to squeeze in something to represent what's happening to the signs. Since the signs are alternating, I need to put a -1 to some power over here. And if we pay attention to how the powers are propagating here, when, like on the second derivative, we see we have a -1 coefficient, so it's negative. On the third, we have a positive. On the fourth, we have a negative. So it's usually in the opposite relationship. So I don't want n in there. I want n minus 1 as the exponent, so that when n is 4, 4 minus 1 is 3, so I end up with a negative. When n is 3, you get 3 minus 1, which is 2, which ends up being a positive coefficient, and so forth on the down line. You could also use n plus 1 if you like, instead of n minus 1. It's an equivalent statement, but I'm just choosing to use n minus 1. All right, so that's the pattern that we see. And we need to evaluate all of this stuff all of these at 1. So I'm just going to, instead of doing each one individually, I'm just going to look at the nth derivative of 1. And the nth derivative of 1 is going to be -1 to the n minus 1 times n minus 1 factorial times 1 to the negative n. But 1 to the negative n is just 1 over 1 to the n, which is just 1 over 1, which is just 1. So this is what the nth derivative looks like at 1. Okay? So keep in mind, if you didn't follow that logic really well, if you plug in 1 here to the x to the negative n, you're still going to end up with 1, and so just everything that was its coefficient is all that's left, which is kind of convenient. All right, so now we just need to go ahead and put all this together and figure out what's going on and see if there are any other patterns we might want to notice. All right, so as we said a little while ago, f of x is equal to f of 1. But f of 1 is 0. I'll put it in there just for a placeholder for now, but we won't leave it in there in the final answer. Natural log of 1 is 0, so that's our constant term here. And then we're going to have, as we said, f prime of 1 over 1 factorial times x minus 1. And then we're going to have f double prime of 1 over 2 factorial times x minus 1 squared. I'm just rewriting this so we can have it. Plus f triple prime of 1 over 3 factorial times x minus 1 cubed, and I'm running out of space. Squeeze in a couple dots there. And so f of x, 0 is gone. F prime of 1, well, f prime of 1 is going to be, if you stick in 1 into our formula that we have right here, our first derivative, so n is 1, so 1 minus 1 is 0, so I get -1 to the 0 power, which is positive 1, and then I get 1 minus 1 factorial, which is 0 factorial, which is also 1. So I'm just going to get 1 over 1 factorial times x minus 1, which just becomes x minus 1. And then I'm going to have f double prime of 1. I should get rid of that plus sign for a moment, which means I'm going to plug in a 2 to n into our formula up here. So 2 minus 1 is 1. And so I got -1 to the first power, so this is going to be negative. 2 minus 1 factorial is 1 factorial, so I end up with 1 factorial over 2 factorial times x minus 1 squared. And I know 1 factorial is 1, but I'm leaving it in there for a pattern for you for a moment. Plus, now I'm going to be plugging in 3 for n, so I'm going to end up with a plus sign. And then 3 minus 1 is 2, so I get 2 factorial over 3 factorial times x minus 1 cubed. And I hope you can see the pattern developing here. The next one will be a minus, and then we'll end up with a 3 factorial over 4 factorial times x minus 1 to the 4th, and so forth on down the line. from here, we should be able to do some simplifying and make this look a lot better than it does at the moment. So let's see if we can do that. We get f of x is equal to x minus 1. And I'm still going to leave the parentheses around that because I like the way it looks like a shift. Now, 1 factorial over 2 factorial. Hopefully you can see how that simplifies. Because if I expand 2 factorial, that's 2 times 1, or 2 times 1 factorial. So this becomes just a 2 left in the denominator. So I really have x minus 1 squared over 2 plus, well, I got 2 factorial over 3 factorial, and 2 factorial is a factor of 3 factorial. So 3 factorial, just make sure everyone's on the same page, 3 factorial is 3 times 2 times 1. But 2 times 1 is 2 factorial, which is going to cancel with the 2 factorial in the numerator, just leaving the 3 in the denominator. And so we're going to end up with, the right color back here, x minus 1 cubed over 3 minus, and the pattern should be evident now, x minus 1 to the 4th over 4 plus x minus 1 to the 5th over 5 plus dot dot dot. The general term, whoops, didn't mean to make that, I'm trying to scroll up a little, plus, well, we're going to have x minus 1 to the nth power, make that look a little better, over n, and then we just got to account for the sign, so I'll need a negative 1 to, well, all the, as we said before, all the even ones, even powers are producing negative coefficients, and all the odd powers produce positives, so I'll put an n minus 1 up here, and then plus dot dot dot. And so this is our Taylor series for the natural log function centered at 1. Now we just need to find the interval of convergence, and so to find the interval of convergence, let's take this general term here and run that through the ratio test. And so with the ratio test, I don't need the negative 1 to the n minus 1. I'm just going to take the limit as n approaches infinity. I still want the absolute value symbols because they do affect x. And then we're going to have x minus 1 to the n plus 1 over n plus 1. And then let's multiply by the reciprocal of the nth term. And so we have n over x minus 1 to the nth power. Close off that absolute value. And then through the magic of simple algebra, at least I would hope we think it's simple, all of those in the denominator cancel with the n of these in the numerator, leaving just a single x minus 1 in the numerator. And so all of this becomes the limit as n approaches infinity, absolute value of x minus 1 times n over n plus 1. Now remember, the x minus 1 is not changing as n goes to infinity, so this is just n over n plus 1, those are the only things we need to pay attention to. And n over n plus 1 heads to 1, and so all of this just works out to be the absolute value of x minus 1. And by the ratio test, for this to converge, we need this quantity, the limit, to be less than 1. So we need all values of x that make this inequality true that we're talking about right over here. And so, just to remind us of what that means graphically, we're talking about an interval, okay? Our interval is centered at 1, and then it moves one unit in each direction from 1. So here's 1 unit in that direction and 1 unit in this direction over here. So any value of x that's in this interval, in the open interval 0, 2, certainly will have this series converge. The only other question we need to consider now is, do we include the endpoints or not? Okay, so we have to run those tests separately, and so to see whether or not we include those. So if x equals 0, what happens? Well, if x equals 0, then we're looking at the sum from n equals 0 to infinity. Let's go back to that general term that we had over here. Our general term, if we plug in 0 for x, we get negative 1 to the n minus 1 times negative 1 to the n. in the numerator, all divided by just n, right? Okay. So we just got to figure out what's happening in the numerator here, because this is going to be either harmonic or the alternating harmonic, or possibly the opposite of the harmonic, meaning the negatives. And we got a little bit of a problem here, which I'm sorry I should have mentioned. Well, not that I should have mentioned it. I just neglected something here. This general statement here is only good when n is greater than 0. So I should have started my series back over here at n equals 1 and not at n equals 0. Otherwise we get division by 0. So don't do that. All right, so, and then the same thing down over here. Got to clean up the mistakes. Anyways, so we get this. Now, if I plug in any value of n, looking at these exponents here, you got n minus 1 and n. One of those is always going to be odd, and the other one is always going to be even. So I'm always going to be multiplying an even times an odd. And so if I multiply an even times an odd, well, no, I'm not multiplying the evens and odds together. I'm sorry. When I raise negative 1 to an even power, I get a positive number. When I raise negative 1 to an odd power, I get a negative number. So one of these negative ones always works out to be positive. The other always works out to be negative. And a positive times a negative yields a negative. So this is always just negative 1 over n. Now we can factor that negative out. And like I said, a possibility was that this was the opposite of the harmonic series. And it is. And so we know that this series diverges. Okay, diverges at, or the series diverges, and so we know 0 will not be included in the domain. Now we just got to check 2, if x equals 2. Then we get the sum from n equals 1 to infinity. And if I plug in 2 here, I still get the negative 1 to the n minus 1, and then I get a positive 1 to the n. Positive 1 to the n over n. That always works out to be just negative 1 to the n minus 1, because 1 to the n is 1 over n. And so this is the alternating harmonic series, and we know that this converges. We already proved that a while back. We used the alternating series test to prove that. And so we are going to include 2 in our interval of convergence. So for this Taylor series centered at 1 for the natural log function, the interval of convergence is the half closed interval 0, 2. And this should make sense, because we should all know that the natural log function is undefined at 0, so that we would expect the Taylor series to be undefined at 0 as well. So that should make some sort of sense in that regard. Now, a phrase that came up in the problem of the week, and a phrase that will be in the textbook, it'll be other places, is a Taylor polynomial. Now, we haven't really used that terminology formally in class yet, so let's make a distinction. So when we have for instance, our sine of x, and we represent it as the Taylor series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... When we're including all the terms of the series, then we're talking about the Taylor series. Or in this case, because we're centering this at 0, it's the Maclaurin series. Okay? But if I change the word series to polynomial, then I just want, say, the Taylor or Maclaurin polynomial. Let me write that down. Then I don't want the whole entire series. I just want up to a certain term. Okay? And so we'll say Taylor polynomial or Maclaurin polynomial of degree n. When we say of degree n, what we mean is we only want you to go up to the x, or the term that has x to that power, x to the nth power. So if I want the 3rd degree Taylor polynomial for sine of x, the 3rd degree Taylor polynomial for sine of x is going to be sine of x is approximately equal to, because I'm not using the infinite sum anymore, x minus x cubed over 3 factorial. This is the third degree Taylor polynomial for, sine of x. I only go up to the third term. There's no plus dot dot here because I'm not taking the whole series. I'm just taking an approximation to it. So the Taylor polynomial is really some nth partial sum where n represents the degree n represents the degree at which we're stopping. Okay, so if I want the fifth degree Taylor polynomial, then the fifth degree would be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Okay, so when you see Taylor polynomial, we're only using a finite number of terms from the series and not the entire series. And so again, it's only going to be an approximation to the series and not an exactly equal to. If we want the exactly equal to, we need every single term of the series. Now, one way the AP examiners like to see how well you understand how to manipulate series is to ask you a question like this one. So what I want you to do is pause the video and try to use any ideas that we've studied, not necessarily only in this section, think outside of this section, and see if you can represent f of x equals sine of the quantity x squared as a Maclaurin series. Go ahead and pause the video and see if you can get that done. Hopefully you were able to accomplish that. And I'm really serious that you should, if you didn't, that you should try this on your own, because if you get stuck, then it's listening to what you should have done that's going to help you get unstuck. But if you don't ever try it, you're not sure if you're ever going to get stuck, and you really won't understand what your weaknesses are. So you got to try this. But assuming you did, hopefully you started by remembering or going back and looking at your notes and saying that, well, sine of x is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot 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 plus negative 1 to the n times x to the, we need an odd number up here, 2n plus 1, all that divided by 2n plus 1 factorial plus dot dot dot. The dots are barely squeezed on there, but hopefully you got it. Well, what we learned in section 8.6 was, one of the things, was if we have a power series representation for some function, and we can relate a new function to this function we know the power series for algebraically, then we can use that algebraic manipulation to generate the power series for the new function we're learning. And so in this case here, we know sine of x, and so sine of x squared, we know the power series, Taylor series, Maclaurin series, for sine of x. Sine of x squared to be obtained just by substituting in place of x, x squared. And so this very simply is just going to be x squared minus x to the sixth over 3 factorial plus x to the 10th over 10 factorial minus x to the 14th. I said 14th and wrote 17th. 14th. And I made a mistake. I'm sorry. I'm getting too much on my patterns. This should have been 5 factorial. And this should be over 7 factorial here. Plus dot 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 plus. We still got the negative 1 to the n. And now we'll have x squared raised to the power of 2n plus 1 all over 2n plus 1 factorial plus dot dot dot. Now all you really need to do is go back in and fix this, and you don't actually need to do this, but what you can do is fix the exponent here by multiplying the 2 times the quantity 2n plus 1 to simplify this. But this is it. This is all you had to do in order to generate this Maclaurin series, because you already knew a Maclaurin series. Algebraically, you could make the relationship like we did in section 8.6. So once again, here is another example. Go ahead and just pause the video and give this one a try. So you need to write down the Taylor series for cosine. So here that is. And then all we need to do is divide everything by x. And so cosine of x over x is going to be 1 over x minus x over 2 factorial plus x cubed over 3 factorial minus x to the 5th over 5 factorial plus plus negative 1 to the n, x to the 2n minus 1, all divided by 2n factorial plus And my bad habit is showing right now, embarrassingly. And so my denominators here are wrong. I apologize. I get to the bad habit of seeing the exponent and the factorial to be the same. I just did it again. There should be a 6 factorial here. I apologize. Don't make that mistake. Don't be like me. Do better than that. One last question for this video, and I got 4 minutes to get this in. So evaluate the indefinite integral of e to the negative x squared dx using the power series. Last year we said that there are not every function has an elementary antiderivative. This is an example where none of the techniques that we've learned for finding antiderivatives would work because there isn't an elementary antiderivative for e to the negative x squared. So this is where we have to use the power of something like a power series in order to make this work. So start by representing e to the negative x squared using algebra as a power series, as a Maclaurin series, and then find its antiderivative. I'm going to pause the video, I'm going to write some of this stuff down and then restart the video so I can make sure I get this in within the time limit of 30 minutes for the video. So this is the power series, or the Maclaurin series, for e to the x. We know that. Now what we're going to do is we're going to substitute in place of x, negative x squared. And again, I'm going to pause the video to write that out. Alright, so here is e to the negative x squared as a power series. And I had to fix something in e to the x because I put plus plus x to the 5th over 5 factorial when I meant x to the n over n factorial, so I fixed that. Alright, now from here, because I want the antiderivative of e to the negative x squared with respect to x, I'm going to take the antiderivative of both sides, and that'll give us the results. Again, I'm going to pause the video and work that out. Alright, here we go. Here's the final answer. So we're taking the antiderivative of both sides, which means we need a constant of integration on one side, which I'm putting on the infinite series side. And so c plus x, antiderivative of 1, plus antiderivative x, or minus rather, antiderivative x squared is x cubed over 3. And then I'm just continuing in the pattern. Plus antiderivative of x to the 4th is x to the 4th over 5. And so the 5 and the 2 factorial need to be multiplied together. And then that pattern is going to continue. And then eventually we'll get to the nth term, which I have on the second level here, or near the bottom. And the exponent just got 1 added to it on x. So x to the 2n plus 1. We've got to divide by that new exponent, 2n plus 1. Still multiplying by the previous factor from the denominator, n factorial. And then plus ... That's got to continue. And that's going to be the final result. So again, on the AP exam, they love to have you do these sort of manipulations. You do have to know how to generate Taylor and Maclaurin series for different functions, but they never get overly complicated. Some of them look awfully similar to what we had to do in the current problem of the week, or have to do in the current problem of the week that you're working on. They look a lot like this, where you're using some known power series, something you already are supposed to know going in, and then doing an algebraic or calculus manipulation on that expression and on that series in order to generate the series for the desired function. And so, yeah, as long as you practice that skill and learn to recognize those patterns, you're going to have a lot of success on the AP exam. Go study.